GTC. Today's talk is on digital twins, which is a new concept in scientific computing. It originated at a SME conference in 2002 with a talk by Michael Greaves, and since has evolved into science in a transformative way. To take us through how digital twins are being used at CERN is Maria Girone. Thank you for joining us, Maria. She is currently the director of the openlab at CERN. Previously, she was CTO. There, she led transformative projects in HPC, AI, and technical architectures. With that, Maria, please take it away.
Thank you. And good morning, everyone. Many thanks for this invitation. Many thanks to Tom in particular. And many thanks to all of you guys for being here to hear about the progress that we are making at CERN, and in particular CERN Lab on digital twins for science. I will be introducing very briefly CERN, but in particular its computing challenges ahead, the way in which we collaborate with science and industry through CERN Lab, and then I will talk about in particular the area that is the topic of the day, digital twins, with a few words about the importance of diversity in technology at the very end. So for those who don't know, CERN is a very special and unique place where to work. Is the European Laboratory for Particle Physics, and also the world, today the world's biggest laboratory. What you see here is the aerial view of the CERN installations. It has got a unique set of accelerators. And the goal that we have is fundamental physics, so it's how to understand the fundamental particles and the laws of the universe. And we do this to answer fundamental questions that we all have: what the universe is made of, how did life begin, and we do this by studying the elementary building blocks of matter and the forces that govern their behavior. We have a set of accelerators that allow us to reproduce the conditions from a fraction of a second after the Big Bang. And like this, we gain insights into the structure of matter, studying the infinitely small to get insights on the infinitely big. Doing fundamental physics requires developing technologies in many areas, but mainly in 3 areas. Accelerators, we're definitely a leader there. But also detectors that are these giant cameras that allow us to understand what we see from collisions. And these are typically largest cathedrals, size of equipment. They are built by consortia from scientists and engineers all over the world. And they produce a lot of data. So high energy physics really a leader in data mining. And we are today already an exascale science. So to process and analyze and select all this data, actually computing is really key. The flagship project that today we have at CERN is definitely the Large Hadron Collider. For the people who have ever been on the ground, this is a magnificent piece of equipment. It's a 100-meter underground, 27 kilometers in circumference. You saw the other view earlier compared to the runway of Geneva. So it's a really very large set of infrastructures. Supercomputing magnets steer the particles, and they are kept at almost the absolute zero, at minus 273 Celsius. And the particles are accelerated very close to the speed of light. There are 4 gigantic detectors that I already mentioned earlier on that act basically like cameras in order to see the results of the particle collisions. There are 2 general purpose experiments, are very big, Atlas and CMS. And they are basically designed in order to do precision measurements of the Higgs boson, but also be sensitive to new physics beyond the standard model. There are two other experiments, ALICE and LHCb, that respectively are dedicated to a certain kind of physics. ALICE for the quark gluon plasma searches a state of matter that may have existed just after the Big Bang, and LHCb that is studying the asymmetry between matter and antimatter that is observed in nature by studying properties of particles containing the B quark. Data mining at CERN is an extremely challenging set of tasks. We start from the collider space where we have collisions for 40 million times per second. We read out millions of electronic signals from these giant cameras. And we have a number of selections and filtering in order to record the data that is most interesting. And we record something like thousands of events per second that then need to be analyzed, reconstructed, and then analyzed. And the reconstruction is this calculation of the physics objects from the detector hits and the energy depositions into the detectors. And at the analysis step, then we compare the data to hypotheses with the simulated events. Now, what really is peculiar nowadays is that artificial intelligence is really used at every step of this data processing chain, from its adoption with edge devices in the very low latency environments that allow us to perform the data acquisition and the first filtering of the data, up, down to simulation, reconstruction, and to the analysis. And CERN is really being a leader in this, adopting deep learning technologies very long ago on analysis. But today, I would say that they are really used everywhere. This is very important because, of course, there's a lot, for instance, that we can develop together with industries, just as an example, in the area of low latency environments and artificial intelligence. So it's quite interesting to see how we actually collaborate also for those endeavors that are outside the fundamental physics itself. The LHC has been really set up to have a series of scheduled upgrades. We are today in the so-called run 3. We have just started the second year of the data taking of the run 3. And until now, we have collected just 10% of the entire data set that is thought to be delivered by the LHC. So we are really at the very early stages of the exploitation of this machine. And actually, what is also very important to keep in mind is that by 2030, 2029, 2030, this machine will be operated at a different regime, the so-called high luminosity LHC, in order to gather the 90% that is missing in the data set. And this is very important on the physics side because like this we can actually provide the scientists with much bigger data sets to analyze, so for greater precision studies and for increasing the discovery potentials towards new physics. But going at the high luminosity LHC also means actually to have the capability of disentangling even more complex events that we have so far studied. And you can see here a comparison between what we have in, for instance, in run 3, with an average of 50 collisions per crossing that we have to disentangle, understand, compared to the average 200 that we are expecting to have at the high luminosity LHC. So I think that you can all gather that to be able to disentangle such complex events, we actually need to really change the way in which we have been doing until now data processing and data analysis. So the upgrade of this machine towards the high luminosity LHC is very important because it's also involving a series of new challenges that are ahead of us. The machine, the accelerator, the LHC itself will be upgraded. There will be a long shutdown to upgrade this machine towards the high luminosity LHC. The detectors will have to be changed, at least in some parts of them, because there will be much more occupancy of the data, as you saw in the previous picture. And the detectors need to be much more granular in order to disentangle this higher occupancy in the detectors. The experiments are also going to open up their selections in order to accept more data. So they are changing the filtering paradigms, and AI is crucial also in these aspects. There's a lot of people doing R&D now in the area of applying AI in edge computing in low latency environments. And in general, in order to be into the resource envelope that you can see in these central plots that is into these black lines, we will actually have to do a lot of R&D in order to be between what we have as a resource projection given our flat budget. So there's a lot of R&D that is happening in the code modernization, in the adoption of high-performance computing. We are a high-throughput computing science so far. Use of hardware accelerators like those that we discuss at conferences like this. Also reducing the storage needs, and definitely the use of artificial intelligence, and farther down the line, even quantum computing possibly. Now, the high luminosity LHC that I'm so proudly talking about is not the only future endeavor that CERN has been taking on. We have already launched a technical and feasibility, a financial feasibility study to develop the future circular collider. Now, this is going to be a very large machine of much larger compared to the LHC that you also see in the picture. The LHC would be the injector to it. Is going to be a tunnel of about 100 kilometers situated between the two mountain chains in the area of Geneva, the Jura and the Salève, going even underneath the Le Mans Lake. So it's a very challenging project ahead of us. And what we're doing today is also setting the scene of what we will have to do in the future, at least for what concerns the challenges in terms of computing. So with all this in mind, collaborating at CERN with other sciences and industry is definitely very important and key. This is why I'm a proud leader of this endeavor that is CERN Open Lab that is fostered in collaboration with the science and industry. Now, CERN Open Lab has been working for more than 20 years now, really in this area of collaboration. We have 4 primary missions. The first, very important, establishing strategic industry collaborations. Second, fueling technological innovation. So talking today about digital twins is definitely important. Exposing technologies to scientists, and this is what we really do when we have projects together with industry. And also, very importantly, nurturing knowledge and growth in young STEM researchers, having a lot of projects and and activities that allow us really to have also young students at CERN, in particular in summer, every summer. Throughout these more than 20 years of collaboration, we have been going in phases of 3 years. This is why, because we really review the major goals that we have in the collaborations with industry. And today, we have just kicked off the phase 8, where we have as main objectives pioneering sustainable and emerging computing and storage solutions for the future of CERN challenges, harnessing heterogeneous computing and AI for a greener future, and of course, fostering synergies and technology exchanges between science and industry. We do this through 2 main R&D directions. One is the sustainable infrastructures, and the other one is emerging technologies. I can't go into details of all the projects that we have in each of these individual activities, but I'm going to cover the one on digital twins, which is really emerging, and we believe that is really key for us at CERN in order to have a way to understand and support the complex infrastructures and installations that we have. You saw earlier on the pictures from the experiments, the LHC. But we have a lot of installations, and adopting digital twins seems to have a great innovation potential in order to really do more efficiently and understand better our installations and our complex processes in science that we tackle at CERN. An example of work that we're doing in the area of digital twin comes from the support of the European Commission. It is called interTwin. It's a project that we have been investing a lot from CERN. Has got three main goals: the co-design and implementation of a prototype for a unified interdisciplinary digital twin engine, using an open source platform and using open standards, and being available to a very large spectrum of diverse use cases from physics and from Earth observation. You can see here at a glance all the use cases that we are supporting. I will cover them in a moment. We have about 30 participants in this consortium, all of course from Europe, because this is funded by a European Commission. And we have leaders in sciences, technology, and resource providers. So it's a very well set project. It is making a lot of progress in the area of the digital twin engine for science. So we have developers for the core engine itself. We have experts from infrastructures, which includes people from and experts from HPC centers in Europe and clouds. Data is served via the modern concept of data lake architectures, and the science researchers access the engine through a user-friendly platform. All is rotating around the main concept of a unified core engine that supports all the digital twin use cases from the different sciences, with access to resources, provisioning in the same group of experts, and of course co-design of a unified engine that will be available to all other sciences. The CERN participates in with its own expertise in key areas such as the core engine for the large-scale AI workflows, the federated data lake infrastructure where we are leading, as we are an by science with a lot of experience in the data handling and data distribution, and a use case specific from high energy physics that is coming from a digital twin of a particle detector. The model simulates detector response from interacting particles using generative adversarial networks for fast simulation to be compared with the state-of-art tools like GEM4. And this digital twin integrates operation conditions for the setups, and is meant also to give a response in real time at the level of detector data acquisition configuration with respect to the different run conditions. This digital twin that we are building, in particular for this detector simulation, is not the only use case from an interTwin on physics fundamental physics. We have a very strong collaboration that involves sciences from the radio astronomy, the gravitational wave experiment Virgo, and the lattice QCD experts. And we also have actually a number of leading institutions that are contributing to the interTwin use cases with, on the climate and environmental sciences side that will allow us to make digital twins for future predictions of extreme events like fires, storms, but also floods and droughts. This is really something that we are very proud of because of the societal impact that we have and the engagement that we have in environmental science. We are also collaborating with the ECMWF, the European Center for Medium-Range Weather Forecast, and the Jülich Supercomputer Center on a project that is called EM32 and is meant to build a large foundation model for atmospheric modeling. It is trained on a large pre-processed data set called ERA5 and is serving downstream a number of use cases from weather prediction on scaling, bias corrections, and now working on the spatial temporal interpolations. This project is an open source project that is offered to scientists and will be also integrated as a use case into the digital twin engine of the interTwin project, so to provide easy access to the HPC resources that are needed for these modeling predictions. So with the experience that we are gaining in this interTwin project that has started almost a year and a half ago, we believe that we have really understood, we are understanding more and more in detail what really are the fundamental requirements for unified digital twins in science. And these are definitely what is important is accelerated computing for large-scale AI-based workflows and support of compute-intensive simulations. So you've seen all the use cases that we have, support of very large models, foundation models, but also requirements are coming from having collaborative developments to support multidisciplinary efforts. And the visualization is another very important requirement in order to provide really policymakers with high explainability. So it's a sort of a way in which I like to say is a sort of a virtuous cycle where accelerated computing serves modern challenges for scientific breakthrough, benefit to society, investment in research, and the circle goes on. Now, the last part, a few minutes, I want to spend on a proof of concept that's been really ongoing very recently with NVIDIA for the integration of NVIDIA Omniverse. You have seen that we have very large infrastructures, and we use extensively CAD models in CATIA format. Some of them have been imported in the USD format. You can see here some of the CAD models that we have. But what is very important is that in this proof of concept, we have demonstrated that we can actually use NVIDIA Omniverse and navigate through installations like this is a beamline with a very nice visualization using NVIDIA Omniverse. And this is a proof of concept that we have been doing in the last few weeks, but we would really like to work a bit more on it and also expand it to many other use cases. We believe that this is really quite a powerful tool that we could also not only use for collaborative visualization of the accelerator and experiment complex, as we have done in this proof of concept, but also use it, for instance, for the detector and accelerator assembly, simulation and integration testing, really trying to, and this is quite a very big potential interest for what we want also to build in the future. Planning could be used. We have a very small spaces and hazardous environments at CERN, where we could also be using digital twins, and also for those activities that have to deal with the robotic applications in confined spaces. We also would like to further do investigations of NVIDIA Omniverse as a visualization tool for instance, our Giant 4 simulated events. So there's quite a lot that can be done, and this is actually bringing me to the last slide. That is not conclusion, but it's really a few words looking forward. We would, what we want to do in the future. So collaborate with NVIDIA via CERN Open Lab to scale up the current efforts will be very important. Consider Omniverse also for its integration in interTwin as a visualization tool of all the scientific use cases that I showed before, in particular in the part of environmental science, and enrich Omniverse use cases towards the future endeavors that we have at CERN that are the high luminosity LHC and the future collider. So one talk about diversity. It is important, and I would like to thank all of the people that are engaged in technology and diversity here in places like this conference, and definitely thank the colleagues from Women in HPC and Ideas for HPC, that is the Swiss chapter. Thank you very much.
Thank you very much. I think we've got time for some questions. I don't think there's a talk after this one in this room. Yeah, there is not. So I think we're okay. Trust me, we're okay. Yeah, question?
There you go. Thank you very much. So you mentioned, I think it was ESP, which was a full Earth environmental model. I can imagine two challenges that you face with something like that. One is that it's hard to explain a neural net's recommendations to policymakers. And then another one is that you have to figure out a way to merge, I guess, your transformer architecture with data. Can you comment on how you approach those two problems?
I think we are at the very early stages of this adoption, so I can't comment on that. But I didn't get the beginning of your question. Was it on the MP2? Oh,
yeah. The question was, how do you explain the results, because the AI, which is basically uncertainty quantification, to policymakers that don't understand the details? Yeah.
How do we explain the results?
Yeah, if the results of the digital twin have implications, the policymakers, how do you explain them, because AI is not tied to first principles?
It's not an easy question to answer. It is really depending on the kind of activity that we are doing. In some cases, now in the case of digital twins, we are really at the very early stages. So, but this is more a wish for the future work that we have ahead of us, rather than concretely what we can do now.
And I think we're out of time now, but Maria will be here for a few minutes before she has to go catch her flight back to Geneva. But thanks again.
Thanks.